our very own professor of theoretical physics, who's going to give us a talk about broken symmetries, Yang-Mills fields, and dark matter. Go ahead, Kevin. Take it away.
Okay, thank you. So the title is Intrinsically Broken Symmetries, Tensor Yang-Mills Fields, and Dark Matter. Let's see, what is happening here? I thought this, there we go. But so the outline is first about intrinsically broken symmetries. And this is an interpretation of standard settled physics, and it's certainly a correct interpretation. It may be new, and it's something students should know about. The rest of the talk is my own more speculative work, and students, I don't know, should sort of pay attention, but I don't think I think there's a very good chance that nature doesn't care about the second part of the talk. And that's about Tensor Yang-Mills fields, a new candidate for dark matter, extension of the Lorentz group to a group called U22, and recovery of the traditional theory in a certain limit. I'm having trouble. There we go. So the two independent symmetries of the action that I've been talking about in the title are general coordinate invariance, which of course is the defining symmetry of general relativity. It acts on tensors and coordinates, but it leaves Dirac indices and Dirac fields, the indices of Dirac fields and of Lorentz vectors unchanged. So here these are Cartan's tetrads. The ordinary metric is quadratic in the tetrads. Here under a general coordinate transformation, we just change the coordinates here, but we leave the indices unchanged. And the tetrads, we change the vector index in the standard way, as treating it as a covariant vector, and we change the coordinates in the standard general coordinate way. On the other hand, the other symmetry that's independent is local Lorentz invariance. It acts on the Dirac fields, on the Dirac indexes, doesn't affect the coordinates, but it affects the components of the Dirac field in this way, where this is a 4x4 Dirac Lorentz transformation. The tetrads transform this way with a standard Lorentz transformation. Now let me see if I can get to the next slide without clicking too often. So the way the fields transform under a general coordinate transformation, again, is that the coordinates change and the vector indices, the world indices of vectors change. The way the theory changes, or the way the fields change under a local Lorentz transformation. Well, first of all, the local Lorentz transformation for a Dirac field is direct sum, where this is a left-handed two-component 2x2 representation of the Lorentz group, and this is a right-handed 2x2 representation. Here, theta is the rotation, lambda is the boost. So that's how that works. And the fields under a local Lorentz transformation transform this way. What's happening here is that most of the work is done by the matrix D, which is a 4x4 Lorentz matrix, the one that I just showed you. The intrinsic reduction of symmetry, well, that's that in the vacuum of, let's look at, first of all, empty flat space, and remember that the standard lambda CDM cosmology is basically flat space with an where space expands. In any event, if we actually talk about flat space without any expansion, then the usual gauge choice is to set the average value of the metric. And I use the term average value, which is the term Dirac introduced long ago, rather than vacuum expectation value. I think vacuum expectation value was an abuse of language. It's just too absurd a term, too many syllables. Anyway, the average value of the metric in the vacuum is in the usual gauge choice. It's just the flat space Minkowski metric. And in terms of Cartan's tetrads, where the metric, of course, is quadratic in the tetrads, it, of course, is eta ik. And the tetrads are usually chosen to have average values in the vacuum that are just Kronecker deltas. This is, again, an empty flat space. But the point here is that these are fields. The tetrads are fields, and they're assuming average values in the vacuum, or in more realistically in the universe. If the universe is described by a density operator, then they assume average values given by that. Now, what we want, of course, is that the average values of the tetrads have to remain invariant under these transformations. These transformations, the general coordinate transformations and the local Lorentz transformations, are independent symmetries of the action, but these are not independent symmetries of the vacuum. And in order for the Cartan's tetrads to remain invariant, one needs that the new tetrad is actually equal to the old tetrad. And that'll be true if this thing is the identity matrix. And what that means then is that if the average values of the tetrads remain unchanged, the general coordinate transformation must be the local Lorentz transformation. Of course, that's a very natural result, but I think it needs saying, I think. And in a universe described by a density operator rho, the average values of the tetrads then are the trace of rho times the tetrad field. And then they're preserved if the general coordinate transformation is related to the local Lorentz transformation by an expression, this expression, which is quadratic in the tetrads. Okay, so this part of the talk, I think, is just probably a possibly new interpretation of settled physics. Anyway, just to restate it, the non-zero average values of the tetrads reduce the two symmetries of the action to a single symmetry, local Lorentz invariance. This reduction of symmetry is intrinsic rather than spontaneous because the tetrads intrinsically have non-zero values. So I'm saying that the symmetry of the action is broken by the vacuum or the space-time of the universe by the average values of the tetrads. And it's like the Higgs mechanism, but I think it's different in that it's intrinsic in a sense. Whereas if you had a slightly different Lagrangian for the standard model, the Higgs field wouldn't have an average value in the vacuum. All right, the rest of the talk is speculative, and nature may or may not care about the rest of the talk. In fact, I don't know. I just, have no idea, but it's consistent and worth mentioning at least. So Tensor Yang-Mills fields. What I'm suggesting here is that the action have a term in it that's that's a Yang-Mills type term. Here, these are tensor Yang-Mills fields that are the bosons that gauge the rotations are called R. The ones that gauge the boosts are called B, and the matrix Li is a linear combination of commutators of Dirac fields. The commutator of two Dirac fields is a generator of the Lorentz. This is invariant under general coordinate and local Lorentz transformations. And what's necessary is that the H be a positive Hermitian field. And that's needed in order to keep the action bounded below. And of course, we surely want that. Equivalently, the energy bounded below. So I'm focusing now on this matrix H and the vector V. What is needed for the gauge field action to be invariant is that under a local Lorentz transformation, the matrix H transform this way. The simplest choice is to let it be a vector field multiplied by tetrads that convert it into a Lorentz vector as opposed to a world vector, and then gamma matrices that turn it into a scalar. Not a scalar, but something that transforms like this. Sorry. The matrix H must be positive in order to keep the gauge field action bounded below. And it will be positive as long as the real vector V is time-like. And I make the vector time-like by adding a second term to its action. This is the extra term. And this turns out to be a mass term also. So I don't know why I'm repeating myself there. Anyway, the action of the vector field then is a normal vector boson action, and then this mass term. The equation of, sorry about that. The equation of motion then for the vector field is this. And you can see that it's approximately zero, but it's not actually zero. There's also this subsidiary condition. This is just the standard way in which vector fields are treated. Now, just as in the Higgs mechanism, you set the Higgs field equal to its average value in the vacuum plus a quantum fluctuation. Here I'm setting the zeroth component of the vector field equal to the mass m that we need, and then a quantum fluctuation, little v0. And I'm replacing, sorry, I'm replacing the space components just by little space components, but there's no change at all. The equation of motion then looks like this. If you expand the right-hand side, in fact, this could have been little v0. In fact, that should have been little v0. So that's actually a typo. And what we see here is that it's revealed then that little v0 is a massive boson. These are terms higher order in V. So from the point of view of what the particle is, basically, apart from interactions, it's basically a massive neutral, a massive neutral boson with mass squared of 2m. And so it's neutral. it's massive and it would contribute to dark matter. So this is the dark matter candidate, the zeroth component of V. And it's properly thought of as a scalar field. The treatment that I think is probably most accurate and logical of massive vector bosons and so forth is that of Weinberg. Of course, I think it's probably true to say that anything Weinberg discussed, he got right and gave probably the best treatment available. Anyway, it would contribute to dark matter, and in the rest frame of the CMB, the average value of this vector field then is M000. The explicitly Hermitian Dirac action density looks like this, and the current that generates the boost field then has no time component unless the tetrads are non-diagonal, because you see the lower index of the tetrads is inside one of these epsilon symbols that only has takes 3 spatial values, and so that means then that the fermions, at least unless the tetrads are non-diagonal, the fermions don't generate a Coulomb boost field, or the boost fields don't generate a Coulomb field from the fermions. Anyway, the others, the Lorentz bosons Ri that generate gauge rotations would generate a Coulomb field, and it would look something like this. And it's then a bit tricky, in fact, very tricky to observe or rule out this effect, because it being a Coulomb field, it would be a modification of gravity, and it would be hard to tell the difference. The modification of Newton's potential would look like this, and experiments put no limits on the masses of Lorentz bosons, no upper limit on the masses, and no lower limits on the coupling. And of course, here, what I'm saying is that these things are massless. The experimental limits look like this. These are the wavelengths of the bosons, and the couplings. Alpha equal to 1 is gravitational strength. So these guys are super, super, super weak. But what's been excluded here in these experiments is basically Yukawa potentials, because, as I said, it's more difficult to exclude the potential of a massless particle because it looks so much like a gravitational field, a modification of the gravitational field. The next topic is whether the gauge field, as I said, the symmetries of the action are general coordinate invariance and local Lorentz invariance. In fact, what I noticed here is that this gauge group can be expanded. The gauge group of the local Lorentz invariance can be expanded to local U22 invariance. And what is the key thing? Well, the key thing is this matrix beta, which is I gamma 0, which occurs in the fermionic action. D, remember, is this direct sum, and it's a clumsy sort of thing that many people don't particularly like. In fact, it's more common many people prefer to instead focus on the left-handed fields which go this way and the right-handed two-component fields which go this way. But in fact, the way fermions show up in nature is really described largely by the Dirac field. And so the question is this direct sum that looks somewhat awkward, is it a hint of larger symmetry? And The key thing about these 4x4 matrices from the point of view of symmetry here is that they leave the beta, which is I gamma 0, invariant. Beta then in this notation is the matrix that has zeros on its main diagonal and two 2x2 identity matrices on its orthodiagonal. Anyway, combining this relation with how gamma matrix, combining this relation with how gamma matrices transform, what we see is that D inverse adjoint beta gamma A, D inverse is you can transfer out the beta and then you get D gamma A, D inverse, and that's the inverse gamma matrix acting on beta gamma gamma B. So what I'm suggesting then is that the gauge group of the Dirac field may be the group of all 4x4 complex matrices U that leave beta invariant. This group has 16 generators, and I didn't really know what it was, so I sent email to Edward Witten, and he replied within hours that it was U22, and it gave us the remarkably simple demonstration that follows on this page. This is a group with 16 generators, and you can see that it's U22 if you just take this equation and you rotate all the 4x4 matrices from the beta direction to the gamma 5 direction. When you do that, you get this expression, and that's the defining equation of U22. So U22 is all 4x4 unitary matrices, or I should say 4x4 matrices that take a complex 4 vector and leave the absolute value of U1 squared, let's call Z1, Z2, Z3, Z4. They leave Z1 absolute value squared plus Z2 absolute value squared minus Z3 absolute value squared minus Z4 absolute value squared invariant. So that's U22. And it's something that includes the Dirac group. It has 16 generators. So this is a huge expansion from the Lorentz group, which only has 6 generators. Now that I think about it, though, I probably should have included some slides showing how this comes about. It basically is that well, there's a paper version of this. Anybody who's curious, send me an email. I'll send you the full version of the paper, which was sent to PRD last week. Basically, the last topic here is Cartan's first equation of structure. So what's often done or often said to be appropriate in quantum field theory is you add all the fields, all terms to the action that are completely symmetric, that enjoy all the symmetries of the action, and are of dimension 4 or less. And in that case, what you'd do is you'd add, you take the covariant derivatives of the tetrads and form a quadratic scalar suitably contracted. And since the tetrads are dimensionless, you have to multiply that by m squared. And so this is another term then in the action. And its equation of motion then is basically that the covariant derivative of the tetrad should vanish. Of course, the tetrads occur all over the theory, so the equation of motion is not simply that the covariant derivative of the tetrad vanishes, but has all sorts of other complicated terms in it, numerous terms in it. But that this term is the one that survives in the limit in which capital M goes to infinity. And that then is the term that says that the covariant derivative of the tetrad should vanish. But that then is one that would then turn the Lorentz bosons into this expression here, which is in fact the defining equation for the spin connection, which is the standard way of doing fermions with in general relativity. So in other words, this formalism that I've been talking about, if one adds a huge mass squared times an integral of the covariance of the suitably contracted covariant derivatives of the tetrads, and then takes the m going to infinity limit, you recover the traditional theory. So I've basically finished here, and so I'll just summarize. The first thing is that the intrinsically non-zero average values of Cartan's tetrads reduce the independent symmetries of general coordinate variance and local Lorentz invariance to the single symmetry of local Lorentz invariance. This reduction is intrinsic rather than spontaneous. Spontaneous being Higgs mechanism. The second topic was that a new and simpler way of implementing local Lorentz invariance, as in Yang-Mills theory, has been presented. It involves spin 2 gauge fields and a time-like massive real vector boson in order to keep the action of the gauge fields bounded below. The massive vector boson is neutral and would contribute to dark matter. It's actually its time component that contributes. The invariances of the action of general relativity with fermions have also been extended from invariance under general coordinate transformations and independent local Lorentz transformations to invariance under general coordinate transformations and local independent U2 transformations. That's a big increase in symmetry. What's motivated this whole work is first to make that I found the spin connection just such an ugly thing to look at, and thought that I've been thinking that it would be really nice to have general relativity look more like Yang-Mills theory that has such a simple structure. Anyway, if the covariant squares, the covariant contracted squares, the covariant derivatives of the tetrads occur in the action multiplied by m squared, then Cartan's first equation of structure holds in the m going to infinity limit, and in that limit, the Lorentz bosons approach the spin connection. So that is basically that. For acknowledgements, I want to mention Charles Boyer, who is in the UNM math department and gave me some group theory information, and Peter van Nieuwenhuizen, who sent me some helpful email a couple of years ago, actually, and then Edward Witten, who explained that the group that leaves beta invariant is U22. So that basically is that. The rest of the slides are just references, and I mean, if you want, I'll show them to you.
Any questions?
So here are the, whoops, well, I don't know, the rest of this, they seem to have disappeared. Right, thank you. So that basically is it. What time is it? I usually give very short talks, and yet once again, I prepare a 50-minute talk and end in 30.